Factorial ANOVA is similar to one-way ANOVA in many ways. As you'll recall, in one-way ANOVA we have a single variable called a factor. The factor can take on several values, which in an ANOVA are called levels. In this example, we have 3 levels of distraction: texting on a smartphone, talking on the phone, or no phone, which I'm calling the control group. The numbers in each cell represent the subject's score in the driving simulator. Higher scores mean better performance. If we introduce a second factor, say time of day, then we have a 2x3 factorial design in this example. There are 2 levels of time of day and 3 levels of distraction. Instead of this study, suppose that our researchers are interested in the effects of alcohol use on distraction and driving ability. They set up a driving simulator and ask the subjects to imbibe alcohol before stepping into it. Set up this way, we have a 3x3 factorial study. 3 levels of distraction and 3 levels of alcohol impairment. BAC, by the way, stands for blood alcohol content. In every factorial ANOVA, we're testing 2 kinds of effects: main effects and interaction effects. Let's first take a look at the main effects. Here I've reproduced the matrix on the last slide, but added a column and a row to hold the averages for each level of each factor. Think of these 2 main effects as 2 separate one-way ANOVAs: an ANOVA for driving skill during the day versus at night, and another ANOVA for driving skill under the 3 different distraction conditions. Just glancing at these data, it looks as if there is no main effect for time of day, since there's such a small difference between the scores for the time of day factor. There is a difference for the type of distraction factor, however, since the means here do show a difference. Let's now look at interaction effects. In this example, I'm not sure that there are any interaction effects. Whether the simulation takes place during daytime or nighttime driving conditions, performance steadily gets better as drivers become less distracted. You can see this more clearly in this graph. The blue line represents performance at night, the orange performance during the day. The square markers represent the scores under the control condition, the triangular ones the scores under the talking condition, and the circular ones the scores under the texting condition. As you can see, the line segments are roughly parallel to one another, which indicates that there's no interaction between the 2 factors. Let's take a look now at another one. This study had to do with frustration tolerance. There were 2 factors: the loudness of a noise and whether that noise occurred under a predictable or unpredictable pattern. Subjects were given a series of unsolvable puzzles, and the number they attempted was recorded over a 15-minute period. That number is the number in each of these cells. As you can see, there was a main effect for predictability, but not for the volume of the noise. In this case, however, there was also an interaction effect. For those in the predictable condition, the volume of the noise didn't make that much of a difference. Both groups attempted about the same number of puzzles. The scores of those in the unpredictable condition, however, varied greatly. Those who experienced a loud and unpredictable noise attempted only half the number of puzzles as those who experienced a soft but unpredictable noise. And you can see this here in the chart. The blue line represents the puzzles solved in the unpredictable condition, the orange in the predictable condition. The round marker shows the outcome for the loud condition, and the square markers for the soft condition. The key thing to look for here is whether the lines are more or less parallel. If they're not, then there's an interaction effect. It's important to remember that factorial ANOVA study can have 1 or 2 or as many main effects as there are factors, and 1 or more interaction effects. Moreover, you can see main effects without an interaction effect, or an interaction effect without any main effects. Let's take another look and approach the problem a little bit. Suppose we had a behavioral program designed to improve the behavior of first graders with ADHD. Researchers administered the program and recorded the number of behavioral incidents over a 2-week period. It turned out that children who participated in the program had fewer incidents than those who didn't, but that the girls benefited more than the boys did. What would you expect the data to look like in this situation? Well, here's one solution. The idea in coming up with these numbers was to show a main effect for the program, which is to say a difference in the mean number of incidents for the program versus the control, while at the same time showing better results for girls than for boys. These numbers meet both of these requirements. Okay, let's talk briefly about calculating F ratios for factorial ANOVAs. The basic concept is the same as for one-way ANOVAs, although the calculations do differ just a little bit. The most important thing to remember here is that for a 2x2 factorial design, we would have 3 F ratios. An F ratio for each possible main effect, and an F ratio for interaction. I hope you found this video useful.